properties. They can be classified on the basis of band theory. So band theories we'll be studying in detail. But before that, regarding conductors, you should remember when you compare resistivity, if you compare resistivity of the materials and resistivity and resistance, these topics you are already aware of from your previous chapters like current electricity. So see, what you have to remember is that regarding conductors, these have low resistivity. If I represent it through rho C, these conductors have low resistivity, while insulators have high resistivity. If I represent the resistivity of insulators through rho I, insulators have high resistivity and conductors have low resistivity. Semiconductors have intermediate resistivity, means resistivity's value varies from conductors to insulators. So the resistivity of conductors will be the least, then we have it for semiconductors, and then highest is for the insulators. Now see, conductivity and resistivity, these are inversely proportional to each other. So if I say conductors have low resistivity, then what would be the conductivity? Will it be high or low?
High.
High. So conductors have high conductivity. Conductivity means conduction of electrons. They are able to pass electrons through them. So if I represent conductivity through this sigma C for conductors, so similarly for insulators, it will be high conductivity or low conductivity? Low. Low conductivity. So now see, regarding semiconductors again, highest conductivity will be for the conductors, then it will be for the semiconductors, and least conductivity will be for the insulator. So these are the order of resistivity and conductivity. Now see, regarding semiconductors, you have to remember two important elemental semiconductors. So two important elemental semiconductors include silicon and the other one is germanium. These two are important semiconductors which you have to remember. Now see, we usually prefer materials which provide low resistance so that we can have high conductivity. But see, as I've told you, electronics, since we are able to study this whole branch of electronics, and semiconductors come in widely use in the industries. The reason behind is that why do we have excessive use of semiconductors? Any idea? Excessive use of semiconductor is available. Why? See, this is due to its ability to control current. We are able to control the current. Means semiconductor devices, these are small in size, these consume low power, these operate at low voltages. And it does not require any cathode heating for the production of charge carriers. So it starts operating as soon as it is switched on. And apart from this, they have long life and high reliability. So mainly due to its ability to control the current. There is excessive use of semiconductors widely in the industry. These have higher semiconductors have a much higher resistivity than metals, definitely, and semiconductors have a temperature coefficient, or you can say resistivity coefficient of temperature resistance, which you have studied in current electricity. So both as negative and high. So that is the resistivity of semiconductors decreases rapidly with temperature, while that of metals increases. And also semiconductors have a considerable lower number density. Number density means number of charge carriers per unit volume than metals. So this is the basic introduction to this chapter. Just note it down, then we'll discuss what is meant by energy gap, energy band. Done all?
Yes, ma'am.
Now see, let us see what is meant by conduction band, valence band. What are bands? So bands are basically closed space energy levels. What is meant by this is that, see, you have already studied atoms chapter. So from Bohr's atomic model, we know that electrons have well-defined energy levels in an isolated atom. So, but due to interatomic interactions in a crystal, the electrons of the outer shell, these are forced to have energies different from those in an isolated atom. So ultimately what happens? Each energy level splits into number of energy levels, which forms continuous bands. And those are what we call the energy bands. Now see, these energy bands are of two types. One is the valence band, the other one is the conduction band. Now see, what is meant by valence band and what is meant by conduction band? Basically, valence band are those bands which are filled with valence electrons. You all must be aware of the term valence electrons from your chemistry classes already. So valence band, these bands, these are the highest energy bands which are filled with electrons. This valence band, this is filled with electrons, and this is the highest energy band. So if I say EV, this will be the energy level band of top energy level, top energy level of valence band. This energy level, this upper line, this is the highest top energy level of valence band. Yes. Now see. Now so highest energy band filled with valence electron is called the valence band. Now see the lowest unfilled energy band. We have one more band with us, which is unfilled. This valence band is completely filled with electrons. But regarding conduction band, this does not have electrons. This is unfilled. So see, conduction bands, these conduction band have free electrons, but these contribute to current. These are not bonded. In case of valence band have valence electrons with them. So that's why this represents the highest level of valence band. Whereas if I say this is the conduction band, if I say this is the conduction band, so this will be representing, this will be the last row of energy level. So if I say EC, so this will be lowest energy level. Lowest energy level of the conduction band. So lowest unfilled allowed energy band, which is next to the valence band. This is called the conduction band. So conduction band have free electrons and the electrons in the conduction band contribute to current. Whereas in case of valence band, these are bonded. They have bonded electrons and these do not contribute to current. So for conduction, what happens? Ultimately, an electron transfers from the valence band to the conduction band for the conduction to occur. That is for the current to flow. Now see, can you see this difference between conduction band and valence band? This difference of energy, see these lines are the energy bands that I've told you, that each energy level splits into number of energy levels. So these are different energy levels. The one which has filled electrons, bounded electrons within it, this is called the valence band. Which has unbounded electrons, which has free electrons for conduction, this is known as the conduction band. Now see the energy gap between these two. This is this gap which you are able to see, the gap between the top of valence band and the bottom of conduction band, in which no allowed energy levels for electrons can exist. This is called the energy band gap, or simply you can say energy gap also. This is energy band gap. So you can represent it through Eg. This is the energy band gap. And all these are various electrons present in the valence band. So energy difference between valence and conduction band gives us the energy band gap, which is also called the energy gap. Clear? No, note it down. Yes, you're done with it? Yes, Fatima, Faisal, Noor, have you completed it?
Yes, ma'am.
Yes, ma'am.
Now see, this is the basic definition for what are conduction bands, what are valence band, and the energy gap between them, that is known as the energy band gap. Now see, we classify insulators, we classify semiconductors and conductors on the basis of these band theory only. So difference between conductors, insulators, and semiconductors on the basis of band theory, what happens? Either conduction band gets filled, or the valence band gets filled, or the energy gap between these two can vary. All three. That makes the difference between all these. Now see, regarding conductors, understand the conduction band in conductors, in case of conductors, if this is the conduction band, so this conduction band is partially filled. This is partially filled with electrons. This is not completely filled. This is not completely empty. In case of conductors, the conduction band is partially filled. And see, valence band is completely filled with electrons. This valence band, this is completely filled with electrons. These lines represent that it is filled with electrons. So conduction, or one more thing can happen. If you see this kind of arrangement, that is valence band that is completely filled and conduction band which is partially filled with energy gap between these two, EC and EV. This is one thing that is possible. Partially filled conduction band and filled valence band. Other thing that can happen is that overlapping conduction band. Means if this is your conduction band, this is another arrangement possible for the semiconductors. So either there is energy gap between the completely filled valence band and partially filled conduction band, or the conduction band and valence band partially overlap with each other. If I say this is the conduction band, this is having electrons, this can get partially overlapped with valence band. So if you see this arrangement, this is the second possible arrangement that the conduction and valence band overlap each other. So this will be EV, this will be EC. So here this represents that the bands overlap. Bands overlap. So in case of conductors, what happens to the conduction band? Is it completely filled? Is it partially filled?
Partially filled.
Partially filled. So conduction band is partially filled. Also, this is first thing that is possible. Other thing is that conduction and valence band can overlap each other. They can overlap each other. Now see, this was regarding conductors. So how can we differentiate it through insulators and semiconductors? Now see, in case of insulators, remember, if this is the conduction band for insulator, this is completely empty. In case of conductors, that was partially filled. In case of insulators, this conduction band, this is completely empty. Regarding the valence band is completely filled. This is the valence band, and valence band is completely filled. Now, one thing that you have to understand in this case is that this is the conduction band, this is the valence band, this will be energy level of valence band, this will be energy level of conduction band. You have to remember that this energy gap which you are able to observe, this EG, this is quite large. This is greater than 3 electron volts. Whereas in case of semiconductor, just the difference that will come will be in this. So in case of insulators, this conduction band. So conduction band is partially filled or empty in case of insulators?
Empty.
Empty.
Right, empty. So conduction band is empty. Regarding the valence band, is it empty or filled?
Filled.
Filled, is completely filled. Valence band is filled with electrons. This is filled with electrons. And one more thing that is important, which makes it different and which differentiates it from rest of the solids, is that energy gap or the energy band gap. This is very large. And you should remember the value that it is even greater than 3 electron volts. So this is the difference that comes in case of insulators. In case of insulators, the valence band is completely filled while the conduction band is empty. And there is a large energy gap which is greater than 3 electron volt between the valence and conduction band. So example for this can be diamond. The energy gap in case of diamond is 6 electron volts. So even an electric field cannot give this much energy to electron to make it jump from the valence band into conduction band. So due to lack of free electrons in the conduction band, insulators are poor conductors of electricity. This is the reason why we say insulators are poor conductors of electricity and do not allow electrons to pass through them because of this gap that has been created. But now regarding semiconductors, this was insulator. Regarding semiconductor, again the conduction band, it will be empty. This will be the conduction band with energy EC. This will be empty. And the valence band will be filled. This till here it is similar to insulators. But see, are you able to observe this very less energy gap? This is what the difference comes in case of semiconductors. The energy band gap, this is very less, and this is less than even 3 electron volts. So this is the energy gap in this case. So again, what is the state of conduction band in semiconductor?
Empty.
Empty. So conduction band is empty. Valence band?
Fully filled.
Fully filled, right. Valence band is fully filled with electrons. Now see, just the difference that comes and differentiated from insulator is the energy gap. So energy band gap, this is less or large?
Less.
Less. This energy band gap is small. And see, it is less than 3 electrons. This is less than 3 electron volts. So you have to remember the energy band gap for two semiconductors, those elemental semiconductors. One, you have to remember it for silicon. For silicon, this value of energy gap, this is 1.1 electron volt, less than 3 electron volt, a proper semiconductor. Second one which you have to remember is for germanium. For germanium, it is 0.72 electron volt. So you have to remember these values. So see, for semiconductors, at 0 Kelvin, the conduction band is empty and the valence band is filled. So the material is essentially insulator at low temperature. However, the energy gap between conduction and valence band is small. That is less than how much?
3 electron volt.
3 electron volt. Energy gap is less than 3 electron volt. For example, energy gap for silicon is given 1.1. This is actually 1.17 electron volt. And for germanium, it is 0.74 electron volt approximately. So at room temperature, some valence electrons acquire enough thermal energy and jump to the conduction band where they are free to conduct electricity. So semiconductors acquire a small conductivity at room temperature, and the resistance of semiconductor would not be as high as that of insulator. Why it won't be as high of insulator? Because the energy gap is quite less, so it will still be able to conduct. In case of insulator, the energy gap was very large, so that's why it wasn't able to conduct, and that's why insulators were classified as poor conductors of electricity. So is the difference between all these are clear? In case of metals or conductors, there are availability of large number of conduction of electrons, because conduction band is also partially filled. So metals have low resistivity or high conductivity. So even a small electric field applied across the metal causes the current to flow through. So that's why for metals or for conductors, this conduction band was partially filled, energy gap was there, or the bands could overlap with each other. So because of the possibility and availability of electrons, conductors are able to conduct electricity through them. They are able to produce current through them. In case of insulators, the energy gap is very large and the electrons are not able to conduct. Because of this, the electrons are not able to jump into the valence band for conduction. So due to lack of free electrons in the conduction band, insulators are poor conductors of electricity. Regarding semiconductors, initially at 0 Kelvin, these behave as insulators, essentially insulators at low temperature. But at room temperature, some valence electrons acquire enough thermal energy and these then jump to the conduction band and are able to conduct electricity. Is this clear? Are the classifications clear on the basis of band theory? Just note it down for me. If you have any doubts, you can ask.
Ma'am,
Yes?
now what about the energy gap for conductors?
Energy gap for conductors, yes, see, there is energy gap between them and these can be overlapped also.
So
Are
there
you
are two
asking the
possibilities.
two possibilities? There are two possibilities. See, depending on the energy gap is zero, large or small, the solids are classified into metals, insulators and semiconductors. In case of metal, the last occupied band, that is the conduction band, this is partially filled with electrons. So two types of band structures are found in metals. So either there is energy gap between the completely filled valence electrons and the partially filled conduction band, as I've showed you, and mainly this first arrangement. This is possible in those metals, alkali metals, lithium, sodium, potassium, all these metals. And the third group, aluminium, gallium, indium, thallium. This arrangement is usually found in those. The second arrangement that is possible is the conduction that is the conduction and valence band which partly overlap each other. They do not completely overlap each other. These partly overlap each other. So here the valence band is completely filled, but the upper unoccupied band is still, this partly overlaps with the valence band. So all those metals, the second group, beryllium, magnesium, these all are shown to exhibit this pattern. Clear?
Yes, ma'am.
Yes, written.
Yes, ma'am.
Alright. So now see, mainly this chapter focuses on this section only, semiconductors. Rest of the basics regarding the classification of solids was this only, mainly based on the valence band theory. Now see, regarding semiconductors, semiconductors are basically of two types. See, first one are the intrinsic semiconductors. Other group that we have are the extrinsic semiconductors. Now, intrinsic are those pure semiconductors we will discuss in detail, and these are the impure. Means these contain impurities on them. And this extrinsic semiconductors, these are also of two types. One we have as the p-type semiconductors, other one we have as the n-type semiconductors, and you must have heard of these terms, n-type and p-type. So basically these n-type and p-type semiconductors are included under this extrinsic conductors only. Now see, before beginning, we'll be dealing with these one by one. Intrinsic, then p-type, then n-type. Before that, you have to understand one concept regarding electron and a hole. This will be utilized everywhere. See, if I say, let's take an example of silicon atom. So it has 4 valence electrons. So if I draw the arrangement of silicon atom bonded to other silicon atoms, it will be in this one. Just make a note and later on write it. Now see, you have to understand what is meant by electron and what is meant by a hole. So this, which to which silicon is bonded, which is making the bond, the covalent bond, this is called the electron. This is definitely the electron. Now see, if somehow I remove this electron, will there be a vacancy created over here? If this electron is removed,
Yes, ma'am.
there will be a vacancy created. This vacancy is known as hole. So you will be using the term in this chapter like this: holes are added, holes are deleted, there are number of holes in valence band, there are no holes in valence band, but actually holes are not any physical quantity. This vacancy of electron is actually the hole that we see. But mainly just to ease our calculation and to ease our understanding, we use and we use or treat these holes as positive charged particles. So what are the negative charged particles in solid? Negative charged particles.
Electrons.
Electron, exactly. Negative charged particles will be the electron and the positive charged particle will be the hole. But just to make you clear that these holes are nothing, these are vacancy or absence of electron in the bond of a covalently bonded crystal. These are called holes. So in terms of band theory, whenever an electron is removed from the completely filled valence band of semiconductor, a vacancy will be left behind. So in the valence band, definitely. So this vacancy serves as a positive charge carrier that we call as a hole. So remember that hole is not a physical entity. A hole is a convenient way of describing charge motion. Though motion can be described entirely in terms of electron only. But you just have to remember that hole is just vacancy created by the removal of an electron from a covalent bond of semiconductor. It is not a physical entity. It has the same mass as electron. Why? Because if electron is getting removed, so whatever was the mass of electron, that will be the mass of hole only, because it is actually vacancy of it. So it is associated with a positive charge of magnitude electron only. So just to ease our calculation, we treat it as if it is a positive charge particle. And one more thing, energy of a hole is higher the farther below it is from the top of valence electron. All right, so these are few characteristics of hole. And what is meant by hole is that these are simply vacancy or absence of electron in the bond of covalently bonded crystals. These are not physical entities. It is just a convenient way of describing charge motion. Understood? So just take it in this way that like negative charges, negative particles will be the electrons and the positive particles will be the home. So just make this tabular form and write down that note point, and we'll begin with this intrinsic semiconductor. Done?
Yes, ma'am.
All right. Now let's start with intrinsic semiconductors. So semiconductors are of two types, intrinsic semiconductors and extrinsic semiconductors. So those pure semiconductor means there is no doping. So we will discuss doping in detail. But first remember the pure semiconductors, these intrinsic semiconductors, these are pure semiconductors. Now see, why do we say these are pure semiconductors? Okay, let us take an example of any atom with +4 valency. Valency is +4, like silicon or germanium. Okay, consider this crystal of semiconductor to be of germanium or crystal. So each germanium or silicon atom has 4 valence electrons, which it shares with the 4 nearest neighboring atoms to form 4 valence bonds. So this each of it, let's say silicon atom or germanium atom, this is tetrahedrally bonded to 4 neighboring other silicon atoms. Like there will be +4 atoms, another silicon atom, or I should write, let me take the example of silicon only with +4 valency. So this is silicon. This is an enlarged view of the crystal. It will be the main major. The central atom will be surrounded with rest of the silicon atom. Silicon I have just taken an example. It can be any other example. So just any crystal of semiconductor I have represented through this. Now see, since it is having plus 4 valency, 4 valence electrons are there in the outermost orbit. So see what will be the arrangement. Let us consider this atom. It will be having, it will be sharing one bond, one electron with this, and one electron of this silicon will be shared by this. That's how a bond is created. If one silicon atom has this electron, other silicon atom has this electron, then these two make bond. From your lower chemistry classes, this is how a bond is formed. If one electron is there, other electron is there. If these two are shared, then ultimately one bond is formed, one covalent bond that you say in chemistry. So see, if this is the electron, say let's say this is the electron of this silicon, this is the electron of this silicon, they will share these two electrons and create a covalent bond or not? Is this clear? Is this representation clear?
Yes, ma'am.
Yes, ma'am.
All right. So see, so this is one atom of this silicon. So it will be having another electron, it will be having another electron, and it will be having another 4 valence electrons in this silicon. Similarly, 4 valence electrons are there in this silicon as well. So what will happen? This will be shared, another bond will be created. Similarly, these are also having their 4 atoms. So these are also having their 4 atoms. So see, this electron will be shared by this. That's how a bond is created. Similarly, it will be sharing its electron with the lowest silicon, and it will be sharing its electron. So this silicon is bonded to all the atoms. Similarly, all these silicon atoms, these will be bounded to each other through covalent bonds. Like this, bonds will be created. One electron of this one silicon atom, making bond formation with the silicon atoms of the adjacent silicon atom. Like this, bonds will be created. Now understand, why do we say, what is the mechanism behind these intrinsic semiconductors? See, if this is one electron, definitely these dots are representing the electron. Now tell me, if I take this electron out, if I have taken this electron, this I have taken and freed this, I have made it a free electron. Initially it was a valence electron. So if it is a valence electron, in which band will it be?
Connection band.
If it's a valence electrons are the
Valence bond.
bonded electron, valence bond. See, it's making a bond. So these electrons are in the valence band. Now, once you free it, then it will go in the conduction band, as one of you was saying. Now, once you free it, once you remove it from the bond, once you break this bond, then we say this free electron, this will be, if let's say we have thermally, we have increased the temperature, and this is a thermally generated electron. Because of high temperature, we have freed this electron. Now tell me, if there is no electron over here, what will be there in this place?
A hole.
Hole.
Hole will be there. A hole has been created. Fine. So one electron went away and one hole was created. Now tell me, if I remove this electron as well, so how many electrons will be removed? If I remove this also and this also, how many electrons will be removed?
2 electrons.
2 electrons.
2 electrons. So how many holes will be created?
2 holes.
2 holes.
2 holes will be created. So that's why we say these semiconductors are pure, because the number of electrons and the number of holes, these are equal. And this discrepancy you will be seeing in extrinsic semiconductors. In one case, the number of holes will be more. In one case, the number of electrons will be more. In case of intrinsic semiconductor, number of electrons and the number of holes are equal. Why? Because the number of electrons that will leave the crystal will be equal to the number of holes which are getting created. So that's why we say intrinsic semiconductors. These are the pure conductors which have impurity less than 1 ppm. And the presence of electrons and holes in an intrinsic is the intrinsic property of a material, and these charges are obtained as a result of thermal excitation. If you free the electron through thermal excitation. And holes, as I have told you, these are essentially the electron vacancy with an effective positive charge. So the number density of electron, this is equal to the number density of holes. Means the number density of electrons is equal to the number density of holes in case of intrinsic semiconductors. So if I represent it through, let me represent it through conduction band. So if this is the conduction band, so I have freed 3 atoms. So these have entered these electrons have entered the conduction band. From where? From the valence band. If this was the valence band, so now 3 holes have been created in the valence band. Why? Initially it was filled. Now I have freed these atoms, and now these free electrons, these are free electrons which will contribute in conduction. All right, and one more thing you have to remember, which, as I've told you, energy band gap. This you have to remember for silicon. This is 1.1 electron volt, and energy gap for germanium, this is 0.72 electron volt, because many a times it won't be mentioned in the question and it will be asking you. So that's why you have to remember. So concept of intrinsic semiconductors are clear? Is clear? Why do we say these are intrinsic semiconductors, and what are the properties exhibited by intrinsic semiconductors?
Yes, ma'am.
Okay. Now see, regarding intrinsic semiconductor, there was a need of extrinsic semiconductors as well. See, there are few limitations of intrinsic semiconductors. These intrinsic semiconductors, these have few limitations. Now see, what are these limitations? Limitations of intrinsic semiconductors. Now see, intrinsic semiconductors, the number of electrons and the number of holes, these are very less. Means the intrinsic semiconductors have low intrinsic charge carrier content concentration. Means number of holes and number of electrons, these are very less. Number of electrons and number of holes, these are small. You can even remember the value that these are approximately 10 to the power 6 per meter cube. In every meter cube, you can see only 10 to the power 6 electrons and holes. So what will happen? These will be having then low electrical conductivity. So this limits the use of intrinsic semiconductors in the semiconductor devices whenever these are used for developing semiconductor devices. Other reason is that the energy gap is large. This energy gap, this is quite large. Energy gap is large. So see, an intrinsic charge carrier are always, and as intrinsic charge carriers are always thermally generated, so flexibility is not available to control their number. And since number of electrons and holes are equal, they can not have predominant hole or electron conduction. So this limits to the usefulness of such materials. That's why in nature we have extrinsic semiconductors. See, regarding extrinsic semiconductors, these are impure semiconductors. Impure semiconductors means they have desired impurity atoms in the crystal. Means in case of intrinsic semiconductors, which we have seen just in the previous section, did we add any atom or did we delete any atom? We didn't do anything. Only the number of holes number of electrons were replaced by number of holes. So see, the process, just understand what is meant by the process of doping. When we deliberately add desirable impurity to pure semiconductor just to increase its conductivity, that process is called doping. So the impurity atoms, all those atoms that are added in the crystal lattice. These atoms, these are called as the dopants. So see, based on these impurity and the semiconductors doped with the impurity atoms, these are called the extrinsic, or these are also called as the doped semiconductors. These are known as the doped semiconductors. So these atoms, which these are deliberately added to desirable to make the semiconductor desirable as to increase its conductivity. So these dopants are also of two types. First one is the pentavalent dopant and the other one are the trivalent dopants. See, dopants which have 5 electrons. Dopants which have 5 electrons. Which have 5 electrons. Where in their valence shell. So if you add any element, if you add deliberately add any element which has 5 electrons in the valence shell, in the valence shell. So if you add any atom which has 5 valency in their valence shell, then we say those dopants are called the pentavalent dopants. First category of dopants is the pentavalent dopants. So they have 5 valence electrons, and examples are those arsenic, boron, not boron, phosphorus. Boron is 3. Arsenic, phosphorus, antimony. These are all the examples of the pentavalent dopants. Whereas in case of trivalent dopants, the elements or the dopants which have 3 electrons in their shell, in their valence shell. These are called the trivalent dopants. So example, from your chemistry, you can figure out boron, indium, aluminium, this whole group of elements. These are which have the valence electron as 3. So these are the trivalent dopants. So is this basic concept clear regarding extrinsic and intrinsic semiconductor now?
Yes, ma'am.
Now see, on the basis of how many purities we have added, which kind of purity we have used, number of electrons and number of holes, we have 2 types of extrinsic semiconductors as well, N-type and P-type. But before that, just note down intrinsic semiconductor and extrinsic semiconductor, then we'll begin with N-type and P-type.
Ma'am,
Yes.
ma'am, that is 10 to the power 6 meter cube or meter inverse cube.
Meter inverse cube means in 1 meter cube, there can be 10 to the power 6 electron hole per meter cube, like this, 10 to the power 6 per meter cube.
Okay.
Yes, written.
Yes, ma'am.
Okay. Now see on the utilization of these pentavalent dopants or trivalent dopants. We have two kinds of extrinsic semiconductors. One we have as N-type, other one we have as P-type. So let's start with N-type first. Now see the dopant that will be used. It has pentavalent dopant. Pentavalent dopant means how many valence electrons?
5.
5. So example you can take, the best example is of phosphorus. Now see if these are doped with atoms which have 4 valence electrons. Like if, let me represent it to you. Let's say I have this phosphorus atom. Initially there were crystal atoms. This crystal lattice was of silicon. Now see, through doping, through some means, I have replaced one middle silicon through this phosphorus. Now see, regarding these silicons, firstly the bond. These silicons, these will be having 4 electrons. So it will be creating covalent bonds using its 4 outermost valence electrons. So see, till here there won't be any change. Now see, regarding phosphorus. Phosphorus will be having 5 electrons. 5 electrons in the valence shell. So see, 1 electron will be utilized with formation of bond with this silicon. Other one will be utilized with the formation of covalent bond with this silicon. The third one, this will be utilized with the formation of this downward silicon. And the fourth electron will be utilized with the formation of bond with this. Now see, we are still left with 1 electron. Are you able to see this? 1, 2, 3, 4, 5. There are 5 electrons in this phosphorus, plus 5. And only plus 4 electrons in all these silicon atoms. The silicon atoms have their octet complete. These have all their valence electrons complete. But regarding phosphorus, we have weakly bonded electrons. This is basically the weakly bonded electron. Weakly bonded electron. This is the weakly bonded electron. Now see, regarding this apparatus, what has happened? We have taken silicon atom, we have taken crystal lattice of silicon atom. And when a pentavalent impurity atom substitutes the tetravalent silicon atom, it uses 4 of its 5 valence electrons in forming 4 covalent bonds with the neighboring silicon atoms, while the 5th electron, this is loosely bound to the impurity atom. Now see, a very small amount of ionization energy, or you can say it gets free at energy of 0.045 electron volt. Let's say at this energy, because 0.01 electron volt ionization energy is for germanium and 0.05 electron volt, I mean this much is for silicon. Since I have taken silicon atom, that's why I've written this ionization energy. So this is required to detach this electron. One thing. So first is through this donor atom, this electron has been freed. Secondly, because of the thermal energy. At room temperature, the thermal energy is enough to set this free electron. So what happens? The dopant atom, this gets converted into an ionized positive core. So as each pentavalent impurity atom donates 1 extra electron for conduction, this is called a donor atom. Why is this a donor atom? Because this contributes to 1 extra electron. So this is known as the donor atom. And these semiconductors have free electrons contributed by these donors. These have these free electrons contributed by these donor atoms. And these are generated by the thermal processes, while the holes are only due to thermal generation. So can you tell me, are the number of holes greater in this, or the number of holes equal to number of electrons, or the number of holes less than number of electrons?
Number of holes are less
Number.
than number of electrons.
Less than. Why? See, we can easily see the number of electrons are greater in this case. So if I represent it through Ne, number of electrons will be far greater than number of holes. So for such semiconductors, you have to understand that as most of the current is carried out by negatively charged electrons. So the semiconductors doped with the donor type impurities. Donor type impurities means dopants are pentavalent dopants. Whenever these are used, the semiconductors doped with donor type impurities, these are known as the N-type semiconductors, where number of electrons are greater than number of holes. Now see, in this you can add few points like, okay, one more thing that you have to remember is that these donor atoms or these impurities these are added, impurities are added in parts per million, ppm, in this concentration unit. And you have to remember one thing that I've just told you, how electrons are generated. So electrons are generated by two mechanisms. First one is through the donor atom itself. Through this donor atom, because it is having extra electron, no hole is there. The other process is the thermal one that I've told you, thermally generated. Thermally generated electron. So since no holes are there. So now see, at this room temperature, thermal energy is enough to set this electron free. So this dopant atom gets converted into an ionized positive core, means hole. This is how electrons are generated. Initially, this atom will contribute to this extra electron, and when the thermal energy is greater, when the electron has gone through the conduction band, then this will be converted into a positive, that is hole. And number of density of electrons is greater than number density of holes. Number density of electrons is much greater than that of holes. These kind of semiconductors, these are known as the N-type semiconductors. Even if I draw the band gap for it, let me draw the band gap as well. Energy band gap. See, if this is the conduction band, this is the valence band, this will be the energy for conduction band, this will be the energy for the valence band. So this is the energy band gap that is between the conduction band and valence band. So see, in case for semiconductors, for silicon and germanium, you just remember that this gap will be equal to 0.01 electron volt for germanium, and this will be equal to 0.045 electron volt for silicon. This is the energy level of donor atom. This is the energy. This is basically the ionization energy that is required. Now see, this was all about N-type. The other type that we have are the P-type conductors, P-type semiconductors. So see, since we use pentavalent semiconductors, in case of P-type, it will have trivalent dopants. So how many valence electrons are there in trivalent dopants?
3.
3. It will be having 3. It will be having trivalent dopants. And the best example you can take is of aluminium. Al plus 3 you write it as. And also this is also added in ppm only, parts per million. Now see, if you have aluminium, first let's say we have silicon crystal with us. This is the silicon crystal. Now see, the center part, the central atom has been replaced now by a trivalent. So let's say it has been replaced by aluminium. Now regarding the bonds. See, these bonds will be same. There won't be any difference in the bonds of silicon atoms. These have 4 valence electrons in their outermost shell, so it will be having it only. Now regarding aluminium, it has 3 electrons in its outermost shell. So 1, it will share with this silicon atom. 1, it will share with this silicon atom. And the other one, it will share with this silicon atom. But are you able to see there is a vacancy? There isn't any electron available to bound with this silicon atom. There are only 3 electrons which have already made bond with these silicon atoms. There is deficiency of electron. So what will happen? This electron, the silicon atom, this will make a bond with this. This electron which is present, this might shift over here to create a bond, and what will be created at this place?
Hole.
Hole will be created. Yes, right. A hole is created. So what happens? Each atom of aluminium actually, each atom of aluminium contributes for hole. So are the number of holes equal to number of electrons? Are the number of electrons greater than number of holes, or number of electrons are less than number of holes? Yes,
Number of holes are greater than the number of electrons.
exactly. Number of holes are very, very greater than number of electrons. So see, such a semiconductor is obtained by doping the tetravalent semiconductor silicon, or let's say germanium, with trivalent impurities, such as indium, boron, aluminium, gallium, all those which you can relate it through your chemistry. And the impurity atom uses its 3 valence electrons in forming covalent bonds with 3 neighboring silicon atoms. And 1 covalent bond is with the neighboring silicon atom, which is left incomplete due to the deficiency of 1 electron. So an electron from the neighboring silicon covalent bond can slide into this vacant bond over here. This can slide into this vacant bond, creating a vacancy or hole in this bond. So this hole is now available for conduction, and we say the trivalent impurity atom now becomes negatively charged when all its valence bond gets filled. Now see, since the trivalent impurity atom can receive electron now, it has created a hole which can receive or accept electron from the neighboring bond. That's why we say these are acceptor impurities, and obviously there are holes created by the acceptor atoms in addition to the thermally generated holes, while the free electrons are due to only thermal generation. So majority charge carriers. What are majority charge carriers in case of p-type conductors? Electrons or holes?
Holes.
Holes. And minority charge carriers?
Electrons.
Electrons. In case of n-type, what are the majority charge carriers?
Electrons.
Electrons.
Electrons. And minority charge carriers?
Holes.
Holes. So are you able to relate? It gets reversed in case of p-type semiconductor. One more thing that remains same, that electrons, no, we say holes, not electrons. Now electrons are not created, now holes are created. So holes are also generated by two mechanisms. See, first is through the donor atom. Other one is through the thermally generated, or not the donor atom, acceptor atom. This is thermally generated. So you have to remember number density of electrons or number density of holes will be very, very greater to number density of electrons. So just write down this part. If you have any doubt, you can ask me. Let's draw the energy band gap as well. If we have the energy band gap with us, this will be the conduction band. This will be the valence band. So EC will be the energy band of this conduction band, and EV will be it for the valence band. EG will be the energy gap. So it will be somewhere over here. The energy for acceptor atom. It will lie somewhere near to the valence band. And again, that I'm not writing again, 0.01 electron volt for germanium and 0.0545 for silicon. Just note it down, then we'll do one or two numericals based on this. Just note it down.
Ma'am,
Yes.
ma'am, could you explain the aluminum, the electron part?
This one, P-type.
Yeah.
No. Now see, regarding P-type conductors, these have trivalent dopants, the impurity atoms that are trivalent. Now see, such a semiconductor is obtained by doping the tetravalent atom. These are the tetravalent and these are the trivalent. Now see what happens whenever you dope with these impurities such as boron, aluminium or gallium. The impurity atom uses its 3 valence electrons in forming the covalent bonds with the 3 silicon. These, and this, and this. These 3 silicon atoms. It has utilized all of its 3 electrons. Now see, one covalent bond has been formed with each of these. Silicon, silicon, silicon. Now see, this one covalent bond over here is still left incomplete. See, this is the first electron, this is the second electron, this is the third electron. So 3 electrons have been utilized in the formation of bond with the neighboring silicon atoms. But still, one is left incomplete due to deficiency of one electron, because here we don't have any electron to make bond with this silicon atom. So an electron from the neighboring silicon-silicon bond, this is silicon-silicon covalent bond. So an electron from this neighboring silicon-silicon covalent bond, it can slide into this vacant space. Now what happens? Now aluminium is able to make bond with this silicon. So now it has completed its all the octets which are available and the covalent bond has been formed. But what about this electron which has slipped over here? Since the deficiency of electron has been created, it means hole has been generated. What does this mean? An electron, when it has slipped, it creates vacancy or hole in this bond. Now this hole is available for conduction. Now this hole
And
is available.
what about the bond between the corner silicon?
This one, no?
Yeah. If the
That's
electron
what
has
I'm
slipped
saying.
over there.
Yes, so this bond has been distorted. That's why number of holes are more. Had this bond been completed with another electron, then we won't be having P-type semiconductor. Then it would be a similar intrinsic type of semiconductor. There is no bond over here now. This trivalent impurity atoms become negatively charged when all of its valence bond gets filled. What happens is that now this is able to receive or accept electron from the neighboring bond. That's why we say this is the acceptor atom. Aluminium is the acceptor atom because it is able to accept electron. But now this bond has been distorted. This bond has been broken now. This covalent bond. This hole, this is contributing in conduction. That's why we say number of holes are more. Otherwise, it would have been intrinsic semiconductor. This won't be a type of extrinsic semiconductor, right? The holes are created by the acceptor atoms in addition to the thermally generated holes. While the free electrons, these are only due to thermal generation. So that's why holes are the majority charge carriers. And the semiconductors doped with acceptor type impurities are the P-type semiconductors. These are the P-type semiconductors because most of the current in these semiconductors, this is carried by the holes which have positive charge. So that's why number of holes are greater than number of electrons. And you should remember that you should note that this doping does not disturb the overall charge neutrality of the semiconductor. In case of N-type as well as in case of P-type, and you can write it down as well, it will be neutral. P-type is also neutral and N-type is also neutral. This does not disturb, this doping does not disturb its overall charge neutrality. Because number of electrons lost, number of electrons hold, these are getting replaced by one another. Is this clear? P-type, N-type semiconductors.
Yes, ma'am.
Yes, done. Have you drawn this band also?
Yes, ma'am.
Okay. Now let's just do some numericals on this. But before jumping on to the numericals, you must understand one formula that is essential for the calculation. See, if I say Ne is the number of electrons and NH is the number of holes. So these are for what? Electrons and holes are excess or less in case of extrinsic semiconductors only. So these represent the part of extrinsic semiconductors. In regarding the intrinsic semiconductors, since we don't have excess of electron or excess of holes, we represent it through Ni only. These are number density for the intrinsic semiconductors. Intrinsic semiconductors. So see, based on this only, these three terms, these have a relation. That is product of number of electrons and number of holes. This is equal to the square of number of intrinsic electrons or holes. Ne into Nh is equal to Ni square. Now, based on this, we have one numerical. This says, suppose a pure crystal atom has 5 into 10 to the power 28 atoms per meter cube. Means number of,
Ma'am,
yes,
ma'am, that relation is only valid for p-type semiconductors or for both.
for both. This is just a relation. This is just a relation between. It just connect. It's an important equation of semiconductor. This implies this fact that for n-type conductor, Ne is necessarily greater than Ni. It just represents this relation.
Okay.
Now see, regarding this question, it says number of silicon atom is 5 into, so number of silicon atoms is 5 into 10 to the power 28 atoms per meter cube as given by the question. Now it says it is doped by 1 ppm concentration of pentavalent arsenic. Now see, number of intrinsic semiconductors given to you, you have to find out number of electrons and number of holes. Number of electrons and number of holes you have to find out. Now see, if it is doped with 1 ppm, it means 10 to the power 6 parts per million means what? 1 part per million means 10 to the power 6 only. So for calculation of number of arsenic atoms, what we can do, we have to understand that silicon atoms are getting replaced by this. So we can say for 5 into 10 to the power 28, we can divide it by 1 million and see how much arsenic atoms are there now, because it is getting replaced by it since it is a pentavalent arsenic. So this will be 5 into, this will be not 16, this will be 10 to the power 6. It is million. Million will be 10 to the power 6. So this will be 5 into 10 to the power 22 atoms per meter cube. So we have a number. So now see, number of electrons will be what? Number of electrons will be contributed by arsenic only, because arsenic is the pentavalent and pentavalent is the donor one. So number of electrons will be simply, then how many number of electrons will be equal to the number of arsenic. The number of electrons will simply be 5 into 10 to the power 22 atoms per meter cube, because number of silicon and number of arsenic atoms that will be there will only be contributing to each electron. So how many arsenic atoms are there will be the number of electrons. So we have Ne with us. We have Ne with us. We have Ni with us. That is 1.5 into 10 to the power 16. As I've told you, one relation to calculate NH. So Ne into NH is Ni square. So NH will be equal to what? Ni square is 1.5 into 10 to the power 16 square divided by 5 into 10 to the power 22. So NH will be 15 into 15. This will be 2.25. This will be 10 to the power 32, 16 into 2, divided by 5 into 10 to the power 22. So 5 into 4 is 20, and 5 into 5 is 25. So that will be 45. This will be 0.5. NH will be equal to now 0.45 into 10 to the power 10. 32 minus 22 will be 10 atoms per meter cube. So using this simple relation, you can calculate the value of holes. Clear? Easy. This is based on the formula. Just write down this first, this relation, or you can actually use this over here. You can use this. You can write this equation under this question. Just copy down this question.
Done, ma'am.
Yes. Yes, Abdullah, any doubt?
Nothing. It got clear.
Okay, fine. So when you are writing down this, no, just write it down. Number of electrons, number of holes, and number of number density of intrinsic elements, intrinsic semiconductor, so that you don't forget it for the next time.
Yes,
It is just representing the recombination, rate of recombination. Yes, yes, no. I can scroll up. Just tell me when you are done. Is this much fine?
Yes, ma'am.
All right.
Done, ma'am.
One small question is there, Abdullah. It's the question is smaller than this, then the class will get over.
okay.
Yes, Noor, should I scroll it down?
Yes, ma'am. I'm done.
Now, just note down this part also, and then we'll do a very small question, which is easier than this one also.
Done, ma'am.
Okay, see, this second question says that there's a semiconductor. This has equal electron and hole concentration. Means initially, this is initially. Hole concentration, this is about 2 into 10 to the power 8 in 1 meter cube. This is how we represent the concentration of holes and electrons. Now see, on doping, Now it has been doped. So now is it an intrinsic conductor, semiconductor, or extrinsic semiconductor? After doping,
Extrinsic.
extrinsic. When initially it was intrinsic. Now since we have doped it, it becomes extrinsic semiconductor. Certain impurity, now what happens? The whole concentration of holes now increases to 4 into 10 to the power 10 per meter cube. On doping with a certain impurity, the whole concentration increases to 4 into 10 to the power meter cube. It has two parts. First one is direct, which you all will tell me, and when I'm writing this part down, answer me in the chat box. What type of semiconductor is obtained on doping? Yes, Fatima and Faisal. Abdullah and Noor have answered. This one is a very easy one. First one. Yes, Faisal, you're also right. Yes, Fatima, you are only there. No, extrinsic. Yes, Fatima, it is extrinsic type of semiconductor. Now you have to tell whether it is N type or P type. Whether this is a P type semiconductor or N type semiconductor. P type. So yes, it will be P type. Why? Because the whole concentration has been increased. Yes, exactly, Fatima. Good. Hole is increased. Since number of holes are increased, this will be P type. Second part says you have to, this is also easy, which we have done. We have to calculate new electron concentration of semiconductor now. See, whole concentration has been given to us, but we don't know now the electronic concentration. So calculate new electron concentration of the semiconductor. We have to find out this. So now see, number of electrons. We have, for calculation of number of electrons, we can use this relation. N in NH into Ne is equal to Ni square. Now see, we have to find out Ne. So Ne will be equal to Ni square divided by Nh. Regarding Ni, Ni is what? Ni is for the intrinsic semiconductor. So look at the question. Tell me what is the value of electrons and
2
holes
into 10 raised to 8.
Correct. 2 into 10 to the power 8. This will be 2 into 10 to the power 8 per meter cube. And for number of holes, it has provided us that it has increased to 4 into 10 to the power 10. So now nothing is difficult. Ni square will be 2 into 10 to the power 8 whole square divided by 4 into 10 to the power 10. This will be equal to 4 into 10 to the power 16 divided by 4 into 10 to the power 10. 4 and 4 will get cancelled. This will be equal to 10 to the power 6 per meter. Clear?
Yes, ma'am.
Okay, so just note down this question as well.